All right, welcome to your first digital lecture. For those of you who were in class on Friday before spring break, you heard me mention that the first online lecture that you'll be looking at today will kind of be a double lecture. I didn't think it was a good idea to go into new material on Friday, so first I will be posting this video, which is the material we were going to cover on Friday, and then there will be an additional material for the regularly scheduled programming for today, Monday, March 23rd. So today, from week 9, day 3, just before spring break, we are going to talk about BiotSavart law, or BiotSavart. Most people say BiotSavart. So BiotSavart law is how we calculate the magnetic field at a given point from a current. And this will be another one of those calculus things. It'll have a similar idea to how we did the electric field from distributed charges, but we will have some additional complexities we'll need to deal with this time. So first, let me draw the situation here. So let's say we have some current or some wire that carries a current I along some winding path. And then we want to know the magnetic field here at the test location. This is similar to the test locations we had with the electric field. This is the location where we want to determine the magnetic field this time, before it was the electric field. And like we did before, we're going to break the source of our field down into chunks and find the field from each of these chunks separately and then add them up in the form of an integral. So here we have this current. Moving charges are what cause magnetic fields. And we are going to have to break this current down into individual little chunks and find the magnetic field at the test location from each one of these chunks. So, switching to green here, we might look at, for example, this little chunk right here to figure out what effect it has on the test location. And there are a couple vectors you're going to need to be familiar with for this bit. One of them is dl. This is the length element, infinitesimally small, along the direction that current is being traveled. This is similar to the L from the magnetic force acting on a wire formula from just before we all parted ways. So this will be tangent to the wire at that point in time. So we have that tiny little bit of length. And that tiny little bit of length is some distance r away from the test location. So this vector will be r, going from the source of the field, in this case a current, to the test location, the location where we want to measure the magnetic field. And then there will be an angle between these two that we will call theta. And that's the angle when dl and r are connected tail to tail. It's the angle between them in those two situations. We'll go with orange. And the idea is that each chunk of length of this wire, and that chunk of length we're calling dl, which is a vector, will create a chunk of magnetic field at the test location. And this chunk of magnetic field, similar to the naming conventions we've given before, is going to be dB. Again, D here standing for a small little chunk of the total. So a small little chunk of the total length is dl. A small little chunk of the total magnetic field is dB. And based on our second right-hand rule, we could say that dB is going to point into the board at that location for the entire length of this wire. So we won't have to worry too much about direction in this situation. So once we have all that squared away, we need to figure out an expression for dB, write it in terms of general knowns and unknowns, and then integrate over the entire length of the wire. So this is the formula we will use for dB. The infinitesimal chunk of magnetic field, or the small chunk of the total magnetic field, is given as some constant called mu naught that I'll define in a second, divided by 4 pi times I dl cross r hat divided by r squared. Or in a form that means you don't have to deal with unit vectors, we could just rewrite this as almost the same expression, mu naught over 4 pi I times dl cross, in this case, just r, and we're going to divide that by r cubed instead. These expressions are equivalent. It's just a difference of do you want to deal with unit vectors or do you not want to deal with unit vectors. And then we will add the whole thing up, or add up the contributions of dB from each little chunk of the total length of the wire by taking an integral. To define this new constant I've put in here, mu naught is going to be similar to epsilon naught. Epsilon naught was the permittivity of free space and dealt with how easy it is to establish an electric field in a vacuum. Mu naught is called the permeability of free space. And deals with the same concept but with magnetic fields. Namely, how easy is it to create a magnetic field in a vacuum? And this has a value of 4 pi times 10 to the negative 7th Tesla meter per amp. And one thing that is very odd about this value compared to all other values in physics is that this quantity is exact. There is no uncertainty in this value. This is kind of a trick of how things are defined, but it's at least an interesting tidbit to know. One other thing about the general definition of BiotSavart law that I could show you is that sometimes your life will be easier than this. Sometimes the direction of dB is very clear. And if the direction of dB is easy to determine and consistent, and what I mean by consistent is each chunk of wire will produce a magnetic field at the test location in the same direction. So from this example picture I have over here, every chunk of wire that you could pick of the wire that I've shown will create a magnetic field into the board at the test location. So we wouldn't need to worry about direction so much. We know the direction would be into the board for every chunk of wire we looked at. So if we want to deal with a situation like this, then we could work in terms of magnitudes. And we could have dB not vector, notice I've left that as a scalar, over 4 pi times I dl, and then the dl cross r hat would just become, in terms of magnitudes, dl times the magnitude of r hat, which is 1, times the sine of the angle between them, and then over r squared. And this expression is probably easier to work with, but you need to have a specific situation on hand in order to use it. So, what this means at the end of the day when we actually find our magnetic field is we will find the total magnetic field at the test location by integrating the expression for dB, either as a scalar or as a vector. So it might look something like this. Mu naught over 4 pi, the integral over the entire length of the wire. Exactly what our limits of integration might look like will depend on our specific problem that we're dealing with. I times dl vector cross r hat over r squared, or the same thing with the other expression I put above without the r hat, with just regular vector r, this time over r cubed. Or, switching back to red, if we're just dealing with magnitudes, we would find the magnitude by mu naught over 4 pi times the integral, again, over the entire wire of, this time, I times dl times sine of theta over r squared. And again, this part will just tell you the magnitude. So, the next step here is to do a couple actual examples, because this is a complicated process and it's easiest to see how it actually works out when we actually have a coherent example to apply everything to. So, I am going to clear off this image, and we are going to do a specific example. And the example that we're going to do, that I will write here in black, is a long straight wire. It is the easiest example, which is why we start with it. So, for a long straight wire, we have the following diagram. We have here our long straight wire carrying a current of I. And we want to know the magnetic field at this location right here. I'm going to label our test location as point P. And to make our coordinate system nice and easy, we may as well make this point here the origin, and put the wire along the x-axis. We can put our axes whatever direction we want, so I'm going to take x is positive to the right, y is positive up, and to make sure we're using something called a right-handed coordinate system, z will need to be positive out of the page. A way to check if your coordinate system is right-handed is to do the x direction cross-producted with the y direction should give you the z direction. And you can check that that's the case with the coordinate system I have shown. But I don't want that on here for the rest of everything. So, we follow the same process as we did before. We're going to break this wire up into little chunks. So, first, I'll imagine considering this chunk of wire. So this is going to be the small chunk of wire we consider. And we need to know something about the direction of the current in this small chunk of wire. So that is this red arrow vector that we are going to call dl. So something you might notice is that this wire is oriented along the x-axis. So our dl, we can just instead call dx for this problem, which will make our lives easier. We're all pretty familiar with integrals over x, but we aren't always very familiar with integrals over L, and they can get a little complicated sometimes. So we'll stick to a nice, simple arrangement here. So, next thing we need to do is label a couple of helpful vectors. the vector r here will go from the small chunk of wire, the source of the field, to the location where we want to know the field, or the test location. And this distance of this point P, from our wire, we're just going to call this R. So we want to know what's the magnetic field at point P and how does it depend on the distance of point P from the wire itself. The only other things we might need here are potentially this angle theta. If we want to use that angle theta, it may be worth knowing that this distance right here is the absolute value of x. I put the absolute value in there because x is negative at the location of the small chunk of wire we're dealing with right now. So now let's see which of our formulas from the previous page we would rather work with. What is the direction of dB at point P? First, from our little labeled green chunk, and then from the rest of the wire. I recommend pausing the video at this point to take a guess about each of these yourself, so you can practice your right-hand rule. So go ahead and pause the video, write down your guess, and then play the video again to check your answer. This is how we're going to do kind of clicker questions and to try to keep these videos as interactive as possible. Welcome back. So, doing the right-hand rule, this is going to be a little difficult to explain without you being able to see me waving my arms around. But don't forget that the magnetic field makes circles around wires. And the only thing left to figure out is the direction of those circles. So everywhere above the wire will have a magnetic field coming out of the board. Everywhere below the wire will have a magnetic field going into the board. So for our small chunk that we're considering that's boxed in green, we will have a magnetic field directed out of the board at point P. And that is what we call dB, the small chunk of the total magnetic field created from this small chunk boxed in green. And it turns out, from the rest of the wire, we get that same direction of the magnetic field at point P. So we have a nice, easy direction of our magnetic field. We can say for sure that the magnetic field at point P is in the positive Z direction. And this means that we may as well not use the definition from the previous slide with all of the cross products. We may as well use the easier one. So we can then start to write out our integral here. So we've got the magnetic field just in magnitudes now, because we know it's going to be in the positive Z direction, equals mu naught over 4 pi times the integral over the entire length of the wire. We'll put actual numbers in here later. I sine of theta divided by r squared times dl, which for our problem, well, I won't put that in yet. We'll show it in just a second. Times dl. So now we need to go about the process of taking any unknown or arbitrary quantities in this expression and writing it in terms of distances we do know. We can write things in terms of I, the current in the wire, x, the location of the small chunk of wire we're considering, r, the distance of point P from the wire, and dx's and dl's. One change we're going to make is to do something with that dl to make it a more recognizable integral, and we're going to change it to a dx because the wire is along the x direction. Then we need to figure out another couple of things. Well, we need to know what r is and what sine of theta is. We need to write those in terms of other variables we know. So r should be straightforward enough, and I'm going to briefly outline this in a horrible yellow color. But this triangle right here is a right triangle, and we can use that for a lot of what we're about to do here. So if we want to find the magnitude of our vector r above, well, that's the hypotenuse of that horrible yellow triangle I just drew and erased. So we can use Pythagorean theorem. Well, one of the legs is x. I'm leaving off the absolute value signs because by squaring it, I'll eliminate any negatives I might have had. And then the other leg has a length of big R, the distance of point P from the wire. So we have an expression for r, and now we need an expression for sine of theta. And don't get confused here and think you actually have to calculate theta. Just remember your SOHCAHTOA. It's more powerful than you think it is. Sine is opposite over hypotenuse. That's the SO of SOHCAHTOA. So if this is our angle right here, whoops, let me use the appropriate color, then that means this side is our opposite and this side is our hypotenuse. So the opposite side is literally just r. And the hypotenuse is the square root of x squared plus r squared. So now we can rewrite our expression for the magnetic field at point P with all of this plugged in. So we have mu naught over 4 pi times the integral, and we'll fill this in a second, of I, well, I is still allowed, and then we have r squared on the bottom. So the r squared on the bottom will become x squared plus r squared without the square root, because the square root goes away when we square r, times sine of theta gives us an r on the top, and then a square root of x squared plus r squared on the bottom. And the only other thing missing was dl, which becomes a dx. So now we need to ask ourselves about the limits of this integral. We need to integrate over the entire wire. So what does that mean? Don't forget to look at your integration variable, which here is our dx. We want to ask ourselves, in terms of x, where does this wire start? Where does this wire end? And if it is a long straight wire, we are making the assumption that it is infinitely long. And it will turn out this is a pretty good assumption as long as the length of the wire is much bigger than this distance r right here. So if this is a long straight wire, we're assuming infinitely long, we will integrate from negative infinity to positive infinity. So our integral is now written, and if this were a timed test problem, this would probably be the end of it. I would want you to be able to write that integral and then move on with your lives. But since this is a lecture video, then we have time to actually evaluate this integral. So I'm going to make a couple simplifications here. One of them is that it turns out this is an even function in terms of x. Whether you plug in negative x or positive x, you get the same answer. So rather than integrating from negative infinity to positive infinity, we can just integrate from 0 to infinity instead and just double our answer. So one of the things we're going to do here is write this as mu naught over 2 pi times the integral from 0 to positive infinity of the same thing. And let me actually do something else as well. We can also pull out the I from inside of this integral. So now we're just integrating from 0 to infinity. Again, this 1 over 4 pi became an over 2 pi because we multiplied by 2 to make this change. And then we have r over x squared plus r squared to the 3/2 dx. And this does not look like a fun integral to do by hand. I'm sure it's possible, but just trust that the result I'm about to give you is valid, and you will have mu naught I over 2 pi r times the quantity of x over the square root of x squared plus r squared being the result of that integration in there. And this will be evaluated from 0 to infinity. So once all is said and done, and there will be a summary page eventually, but the magnetic field from a long straight wire is going to be, well, when x is infinity, turns out this is a slightly difficult integral to evaluate, because we have an infinity over infinity, but you can, since you are not required to do this yourself as part of this class, you can just trust this result or verify it yourself, or come set up an office hours appointment with me if you would like to see it worked out. Mu naught I over 2 pi r. And this is the magnitude. You will find the direction from our right-hand rule, specifically right-hand rule number 2. And the long and short of this is that the magnetic field, like we've mentioned before, makes circles around the wire. So if we had a wire carrying current to the right, we could say with confidence that above that wire, the magnetic field will be out of the page, and below that wire, the magnetic field will be into the page. Or, to draw this another way, let's imagine we are looking at a current that flows directly into the board here. So the current is flowing away from you and perpendicularly into your screen. Well, the magnetic field will make circles around the wire, and the direction of those circles is determined by the second right-hand rule to be, in this case, clockwise. So at any given location on the near this wire, say right here, we would draw ourselves a tangent line to that circle and choose the direction that matches with the way that B is rotating around the wire. So in orange we have magnetic field lines in diagram form, and in pink we have magnetic fields at specific locations. So these bits in pink are the magnetic fields at the location of the tail of that vector. So just to be really clear about the assumption we're making here, we are assuming an infinite wire, which is true when L is much, much greater than R. L being the total length of the wire, and R being the distance away from the wire that we want to know the magnetic field. So if we have a 1 meter long piece of wire and we want to know the magnetic field 3 centimeters from the edge of that, from one side of the wire, that would be a situation where we could use this formula. It would be a great situation for it. For much, much greater than, look for a factor of at least 10. But if we had a 1 meter long section of wire and we wanted to know the magnetic field a distance of 1 meter from it, well, now R and L are both 1 meter, and we would not want to use this equation. We would want to, in that case, go through the entire BiotSavart law process and come up with an integral that gives us the magnetic field we specifically want. So, clearing this all off real quick. This means we can now do magnetic field superposition problems. I heard the groan all the way from every time zone which you all currently call home. So if we had, for example, a current here going into the board, and a current here, we'll call I2, coming out of the board, and we have a wire going, we'll say to the left this time, carrying current I3, and we want to know the magnetic field of the location of this X. Well, we'd have to kind of look at each of these separately. So I'm going to do I1 in blue here. I will do I2 in green. And I will do I3 in red. The assumption is that these are all long straight wires that are long enough that we could use the formulas from the previous page. So from wire 3, well, above the wire, the magnetic field would be into the page. Below the wire, the magnetic field would be out of the page. So up here at our test location, we would have, just a second here, trying to figure out where to draw this, a magnetic field directed into the page. I'm going to need to move that label. Caused by just wire 3, where this distance here would be the R value you would need for that equation. Then, from I2 is going to be the next easiest one to draw. Well, we know this distance right here would be the R value in question, and our magnetic field is going to make circles around the wire. So our magnetic field will be perpendicular to this line that I just drew representing R. And we just have to use our second right-hand rule to figure out the direction, and I get that the direction of magnetic field 2 should be to the right. And again, this always has to be a right angle. I apparently did not plan out the location of my labels very well. Last but not least, for I1, oh, that's not a straight line at all. There we go. That'll work. This distance would be the R that you would need. And again, our magnetic field will be perpendicular to this using the results of right-hand rule number 2. We can figure out that the magnetic field B1 will point in this direction, again, where this is a right angle. And you might have to do a little bit of trigonometry. For example, if you want to split these into vector form by first finding the magnitude and then doing some SOHCAHTOA, you can check the geometry yourself, but that angle theta and that angle theta are identical to each other. So we know a few things at least from this. if we use our standard coordinate system with x is positive to the right, y is positive up, and z is positive out of the board, then we can say that B1 will have a negative x component, a negative y component, and 0 z component. We could say that B2 will have a positive x component, 0 y component, and 0 z component. And we can say that B3 will have 0 x component, 0 y component, and a negative z component, since B3 goes into the board, and into the board is the negative z direction. So to proceed in this problem, I recommend finding each of these magnetic fields separately. If you want to do the cross product way, you can. It'll make it in vector form already for you, but it might be more of a pain than it's worth. But you can find all of these magnitudes of B1, B2, and B3 separately, break them into components using trig and just knowledge of what direction these vectors point, and then add them all up separately in the x and y directions using a table similar to something we've seen before with x, y, and z components, where we're going to add B1, B2, and B3, and that will give us the total magnetic field, where we add up each component separately. I would recommend my YouTube channel right now, or after today's lecture. There is a video on there that could be helpful for some of this stuff. It is entitled Magnetic Field Superposition. I recommend using that video as a practice problem after you've completed this lecture. So go on there, start the video, see what the problem statement is, then pause the video and try it yourself, the entire problem. And then once you're done, once you have an answer, watch the video and use my work as a solution for your work to see how good you did and how close you got to the correct answer. See if you can address any of the mistakes you made by watching the video. And if you have any lingering questions, email me and we'll set up a time for a digital office hours meeting. So the last thing for today is to do BiotSavart law again, this time with a circle of current, or a current loop. So this is going to be a little confusing to draw. I'm going to do my best. So this is our circle of current, with this being the center, which we're going to put at the origin. And current flows around this way. And we are going to attempt to find the magnetic field a distance of r directly above the center of this circle, perpendicular to the surface of the circle. Oh no, that should not be labeled as r. This should be labeled as y, because the radius of this loop is now r. So one of the things we should figure out is if there's a nice, easy way for us to determine the direction of this magnetic field. And we could consider a couple different little chunks of current. So for example, this chunk of current right here has a dl that goes into the page. So effectively, dl is going this way, but with the perspective of this drawing, the current is going away from you as it rounds this corner and will be coming towards you as it rounds the other corner. And then we will have a corresponding, back to green, r vector going out this way, and then our magnetic field will be perpendicular to this r vector. So flipping back to the formula that we've been using, dl cross r. So dl goes into the board, r goes up and to the left, leaves us with a dB pointing this direction that is perpendicular to this r vector. Now, to show why this actually helps us and makes our life easier, let's consider a small chunk of current on the opposite side. Here, your DL will be coming out of the board straight at you, or kind of attempting to draw this on our diagram this way. We will have, again, an r vector. The r vector comes up this way, and dl coming out of the board cross r gives us a magnetic field dB that points this direction, again, perpendicular to the r vector. And just to make one of the angles here clear, this angle, theta, is going to be identical to this angle, theta, up here. So look at this carefully for a couple minutes and let me know what you think, or let yourself know what you think about the x, y, and z components of the magnetic field at that test location, using the same coordinate system as before. Is there anything you can think of about the direction of the magnetic field there? Yes. So it turns out here that Bx and Bz are going to equal 0. So with these two chunks we've seen right here in green and blue, both of them have 0 z component, but they do each have an x component. But whatever x component we get from the green one in the positive x direction is perfectly canceled out by the x component from the blue one in the negative direction. So those two components cancel each other out, and that will be true all the way around the circle. For any location on this circle, there's a location on the opposite side of the circle so that all of the magnetic field components except y cancel out. So we are trying to find a magnetic field that will be in the y direction, specifically the positive y direction for this arrangement. So since our direction is nice and simple, the easiest thing to do here is to deal with a nice simple version of our dB formula, and the one with just magnitude, since we already know the direction. So that's mu naught over 4 pi times I times dl times sine of theta over r squared. So we need to come up with expressions for some of these terms. One of them, r, is easy enough to determine, again, from Pythagorean theorem. I'll show you the triangle I'm going to be using in yellow before I immediately erase it, because yellow is a stupid color. So that's the triangle I'm going to be dealing with. It is a right triangle. Sorry if that yellow is a little hard to see. I'll pick better colors for future videos. So we can write that r is equal to the square root of y squared plus big R squared. Cool. Then we need to figure out how to write cosine of theta. Wait, not cosine of theta. What am I doing? Sine of theta. But keep in mind, this theta right here is not the same thing as the pink theta I have labeled above. This theta, this red theta in this equation right here, is I'll label this, is the angle between DL and R. So note that for the green one, for example, DL is into the page and R points up this direction. It turns out that this angle for every point on that circle is actually 90 degrees. So our sine of 90 degrees will be 1. So let me rewrite my expression for dB here a second. So dB is now mu naught over 4 pi times I times dl, which we haven't figured out what to do with. Sine of theta is just 1 over y squared plus r squared, where the square root disappears because we squared our r value. But keep in mind, this is the entirety of dB. And we don't want the whole thing, because we know that dB is in the y direction. So we only want the y component of this. So we want to find dBy, which will turn out to be regular old dB times the cosine of theta, where this theta, now that's the pink theta we have labeled in our pictures. So we can find an expression for cosine of theta as being adjacent over hypotenuse. And that becomes r over the square root of y squared plus big R squared. So now we can rewrite our formula for dB as a formula for dBy is mu naught over 4 pi times I times R times dl over y squared plus r squared to the 3/2 power. Well, now we need to figure out what the heck to do with dl. We've been ignoring it so far. So, what to do with dl? So it turns out this current is sometimes in the x direction, is sometimes in the z direction, sometimes in the negative x direction, sometimes in the negative z direction. So there's no one single dx, dy, or dz in this case that we can actually apply to this dl. So we're going to have to get a little clever. One way we could do this is to define dl as an element of arc length, where you could say dl equals whatever the radius of the circle is times d phi, where phi would be this angle down here. So you could do that, and that will actually get you the same answer. If you're planning on becoming a major in physics, that might be something to work through to make sure you can. But I think there's actually an easier way. And let's write out our integral from by to see what. So we're going to have the integral over the entire wire of mu naught over 4 pi times I times R times dl divided by y squared plus r squared to the 3/2. And now let's pull everything out in front of this integral that we can. So Well, mu naught and 4 pi are constants. The current is a constant that doesn't depend on which chunk of the wire we're considering. Big R is a constant that doesn't depend on which chunk of the wire we're considering. And so is Y. The value of Y is going to be the same no matter which chunk of R or which chunk of the wire we're considering. So all of that is constant and can be pulled out of the integral, and we're left with the integral of the whole wire of dl. So when you have an integral like this, for example, the integral of dx from, say, 1 to 7, this just ends up being 6. So it's the amount of total x that you cover going from 1 to 7. So what we need to ask ourselves here is how much L do we cover as we go around the entire wire? And the answer is, pause it if you want more time to think, but the answer is that the total length of the wire is its circumference, 2 pi r. So that whole integral over here, this part boxed in orange, is just 2 pi r. So we can now write our final formula here. So the magnetic field for a loop of wire is mu naught times I times the radius of the loop of wire squared divided by 2 times y squared plus r squared to the 3/2 power. Or an equivalent expression at the center of the loop. Is mu naught I over 2r. Again, these are just giving you magnitudes. You will again have to get the direction from right-hand rule number 2. But luckily, the direction will be consistent along this entire central axis that goes through the wire. Anywhere along this whole yellow line, the direction of the magnetic field will be the same. If you want to know how would you find the magnetic field at a location like out over here where I've put this yellow dot, that would still be BiotSavart law, but it would not be an integral that were so easy to evaluate. So we're not going to do situations like that. It's something you might see as a physics major. So, just to kind of clarify things a little bit and summarize the formulas that we've learned today from BiotSavart law. So we've got BiotSavart law, the actual law itself. Give me just a second here. Where we can find our magnetic field at a given location by adding up the contributions from the entire wire of the magnetic field from each individual chunk, where we defined that magnetic field from the individual chunk of wire is mu naught over 4 pi times the current times dl cross r hat over r squared, or just in terms of magnitudes, as, again, mu naught over 4 pi times I times dl times sine of theta over r squared, where, to be clear, this theta is the angle between dl and r. And then we have the formulas we derived from the BiotSavart law. So, one of them is the magnetic field from a long straight wire. Which is mu naught I over 2 pi r, where, just to clarify here, this r is the distance of the test location from the wire. And we are assuming that the length of the wire is at least roughly 10 times greater than that distance r. We have the magnetic field from a loop of wire as mu naught I r squared over 2 y squared plus r squared, quantity to the 3/2 power. And the magnetic field at the center of loop of mu naught I over 2r. You might more properly call this one above on loop axis. Where, just to clarify the different definitions of r here, these r's are the radius of the loop, and y is the distance of the test location from the center of the loop. Again, I highly recommend you see my YouTube channel. There should be a link, I believe, from back in the day on Piazza, or there's one in your email as well. I think if you just search for YouTube and emails for me, you should be able to find it. If not, just email me and I'll be happy to post that link again. But the relevant video on there is called Magnetic Field Superposition, and it would be a great practice problem to see if you are comfortable using these formulas in green that we have derived today. The other thing you should be able to do is to set up a BiotSavart integral in a simple situation where the symmetry of the situation is very nice. So, that is everything. I will have a second one of these videos posted that will be the official week 10 day 1 video. Again, this is the delayed material that we were supposed to do the Friday before break that I decided not to do on that day. So that should be everything. Have a good day. Don't forget to reach out to me by email with any questions that you have, and I am more than happy to set up one-on-one appointments with people through Zoom for digital office hours if anybody has any questions. Good luck, and continue to bear with us as we figure out how to deal with this unexpected situation. Thank you. Have a good day.